The difference between 6.1 and 6.2 is that 6.1 used large samples, 6.2 uses small samples. So when we have small samples, we can't use the normal model. We have to use something called a t-distribution. Okay? So t-distributions are when the population standard deviation is unknown, the sample size is less than 30, and the random variable is approximately normally distributed. So those are our three conditions. We have to make sure that those are satisfied. So if your sample size is small, then you have to do this. Since doesn't follow a normal model, it follows a t-distribution instead of a normal distribution, we have to find critical values for a t-distribution instead. So for the normal model, we use the z sub c, the critical value for the z-score. Now, for the t-distribution, we use a t sub c, or the critical value for the t-distribution. The properties of a t-distribution are somewhat the same as a normal distribution. The mean, median, and mode are all equal to 0, just like the normal model. It's still bell-shaped and symmetric about the mean. The total area under the curve is still 1, but the main difference is that the tails are thicker than the normal standard distribution. Okay? A standard deviation, another main difference is that the standard deviation of the t-distribution varies with the sample size. Okay? That standard deviation varies creates a family of curves that gets used, and the family is determined by the size of the sample, which determines the degrees of freedom. The degrees of freedom which we say lowercase d sub f is equal to n minus 1. Okay, so what happens is that as the degrees of freedom increase, your sample size is going up. So the tails being thicker become thinner, and it resembles more of a normal model. So in this picture, the blue curve is the standard normal curve. Okay, that has thin tails. It's really thin right here and thin right here. But as, say, the degrees of freedom are 5, the tails get a little bit thicker. And if the degrees of freedom get even smaller, where it's even 2, then they're thicker than that. So the lower the degrees of freedom, the thicker the tails. Okay? So again, your normal model would look like this, and your t-distribution has thicker tails. So thicker tails. And the thickness of the tail depends upon the degrees of freedom. And as n approaches 30, the t-distribution approaches the normal distribution. So that's one important thing to remember. As n gets bigger and approaches 30, you'll be able to use the normal model. When we're finding the critical value for a t distribution, we have to use tables to give us that critical value. Okay, so suppose that I was trying to find the critical value t sub c for a 95% confidence level, where the sample size is 15. That means n equals 15. Remember, our degrees of freedom formula is n minus 1. That means it would be 15 minus 1, or 14. So we look under the degrees of freedom column, we look for 14, and that gives us, for a confidence level of 95% confidence level, that's going to give us 2.145 for our critical value for our t distribution. So you're going to have to use the tables in the back of your book to find those critical values. So when you have a t distribution, when you're trying to construct a confidence interval, okay, first of all, check and see that the standard deviation is not known. The population needs to be random, and it needs to be normally distributed, or n has to be greater than or equal to 30. Okay. You find the sample statistics, you've got to find that mean. Actually, this should be n is less than 30 in order to use a t distribution. Okay, find your sample mean, identify the degrees of freedom, and then find that critical value using the tables in the back of your book. Then find your margin of error. It's the same exact formula, except that it has t sub c instead of z sub c. And then find the interval, which is the same exact formula also. Okay, let's put it into practice. You randomly select 16 coffee shops. That means n equals 16. And you measure the temperature of each coffee sold at each. The mean temperature of the sample is 162 degrees Fahrenheit, with a standard deviation, sample standard deviation of 10. We know that they want a confidence level of 95%. Find the confidence level, assume that they are normally distributed. So we randomly selected and they're normally distributed, so our conditions have been satisfied. We also don't know our population standard deviation is unknown. We know our sample standard deviation, but not our population standard deviation. That means that since this is unknown, we're going to proceed with a t distribution. Our degrees of freedom are 16 minus 1, or 15. Our margin of error is going to be our critical value times the standard deviation of the sample divided by the square root of our size, which is 16, times our t sub c. We have to use a table to find our critical value using 15 degrees of freedom and 95% confidence level. We get from the table that it is 2.131 is our critical value. That means that our margin of error is plus or minus 5.3275. Plugging that into your calculator. That's our margin of error. Okay? Now to find the interval, we have to take our estimate, which is x bar minus e is less than mu is less than x bar plus e, which means 162 minus 5.3275 has to be less than mu is less than 162 plus 5.3275, which means our interval is from 156.67 up to 167.33. That's our confidence interval. That means we need to relate that in a sentence in context, which will say we are 95%, because that was our C level, confident that the mean temp of the coffee sold was between 156.67 and 167.33 degrees Fahrenheit. Remember, you can use the calculator to calculate this also by going to Stat, move over to Tests, do a T interval, your T interval, within your T interval you want to use your stats, and you want to put in your X bar, which was 162, our sample standard deviation was 10, our N was 16, and our C level was 95. And when you calculate it, you're going to get exactly that same interval.